The next topic which we'll be beginning today is integers and algorithms. So as we have already seen what we mean by algorithms. So algorithms are basically a sequence of steps. So these sequence of steps or the procedures we perform arithmetic operations on sequence of steps by we perform arithmetic operations by using sequence of steps based usually on decimal representation of integers. So that is base 10 representation, decimal representation of integers. So basically what we do is we always perform arithmetic operation, that is algorithms are a sequence of steps by which we perform arithmetic operations, addition, subtraction, multiplication on decimal representation. So whatever algorithms we have seen, sorting, searching techniques, all of them were on integer values. Apart from that, whenever we are speaking about computer arithmetics or whenever we are speaking about the usage in CPU, the usage that is usually done of numbers is binary numbers. And apart from that, we even have octal and hexadecimal numbers. So these are the different number systems which we use in computer systems. And later, in the later times, algorithms were also used along with these number systems. That is, algorithms were adapted for binary numbers, octal and hexadecimal numbers. So for these reasons, we will discuss these number systems in this section and also the conversions of these number systems. So in everyday life, whenever we are speaking about number systems, we generally use the decimal notation to express integers. That is, suppose if I am taking an example of 765, then it can be represented as 7 into 100 plus 6 into 10 plus 5. Or 100 can be represented as 10 square plus 7 into 10 square plus 6 into 10 power 1 plus 5 into 10 power 0. So basically, whenever we are representing numbers, they are used with a convenient base. So 765 belongs to the base 10 representation or the decimal representation. Apart from that, we use the binary notation. The binary notation's base, if you remember, it is 2. And we have octal with base 8. And lastly, we have hexadecimal with the base 16. And these notations are used to express characters, letters or digits. In fact, any positive integer greater than 1 can be used as the base. So we can even have base 15, 12, 24, any base can be used. Now, for this, we will see a general formula which is used for the representation of base. So, whenever we are talking about the base B number system, any integer greater than 1 can be used as a base. Ordinarily, we write base 10 representation of numbers using digits 0 to 9. Of course, any base greater than 1 will work. For any positive integer n, comma b, there is a unique sequence of numbers and the expansion is done in the way that I have shown earlier. Now, what is the formula that can be used? So, base b expansion of a number, let b be a positive integer greater than 1. Then if n is a positive integer, it can be expressed uniquely in the form n is equal to ak bk plus ak minus 1. This is actually power. So this is b power k the first term if is multiplied by the same. So if you have a number 765, so this is your 0th term, first term and second term. So second term will be multiplied by that power only. So the base is taken with that power only. So if you have taking the base 10, then we multiply 7 with 10 square. Similarly, the k minus 1th term is multiplied with b power k minus 1, and the last term with b power 1, and after that b power 0, or we don't even need to mention it, where k is a non-negative integer and a0, a1, ak are non-negative integers less than b, and ak is not equal to 0. Okay, now for this, to understand this, we can take an example. Before that, let's see the different important bases that we have already seen. So base b, which is equal to 10, is decimal. So there, in the case of decimal numbers, how many digits we will have? We will have 10 digits, 0 to 9. Similarly, with base is equal to 2 for binary, they will have only 2 digits. So if the base is equal to 10, then that will be the number of digits we will have in our number system. Why do we have 10 digits? Because we generally used it in earlier times, and for that reason. Now base b is equal to 2. It is used in modern computers, and we have only 2 digits, which are known as binary digits, bits. After that, we even have base b 8, which is octal. So we will have digits from 0 to 7. And when we are speaking about hexadecimal, we will have 16 digits, 0 to 9, and then a to f. And usually hexadecimal digits are corresponding to 4 bits, while octal digits correspond to a group of 3 bits. Now let's see an example for the same. Suppose, let's talk about binary expansions. So I am given a binary number 10101 and then 4 ones, which is a binary number. So the base is 2. Now I want to convert it into decimal value. So I want a number with base 10. What will be the solution and how are we supposed to do it? If you just remember the theorem that we have seen, so let's give it the values. So this will be 0th value, first, second, third, fourth, fifth, sixth, seventh, eighth. So there are 0 to 8 digits. Now if the position at the eighth position should be multiplied with base power that value. So we have to multiply it in this way. So we will write it in this way. Is equivalent to, so the base is 2. 1 is at the 8th position. So 1 into base power 8. 1 into 2 power 8. After that 0, which is at the 7th position. So we have to multiply with 2 power 7. Then the the 6th one, 1 into 2 power 6, 0 into 2 power 5. I'm corresponding the base with these values, the one which are written below. Then after that 1 into 2 power 4 plus 1 into 2 power 3, 2 square, 2 power 1, and then lastly 2 power 0. So this can be written as 256 plus 64. This is 0, so the ones which are 0, let me just cancel it. So this is 0, this is 0. And apart from that, 16, 8, 4, 2 and 1. So the answer will be 351. Okay, so this is the binary expansion of a number, which is given as follows. Similarly, apart from that, we can also do hexadecimal expansion and octal expansion. So let's do hexadecimal expansion. So we are performing hexadecimal expansion and converting that into a decimal number. So for hexadecimal expansion, 16 is the base used in computer science generally, and this is used for representing characters, letters, etc. And the 16 digits, as we have seen, are from 0 to 9 and A to F. So A to F, what does it represent? A will represent the number 10, A represents the number 10, B represents the number 11, C 12, D is 13, and E and F are 14 and 15. Now we will see an example. So the number given is 2A E0B and the base is 16. We are supposed to convert it into a base 10 number. Okay. So now first again we have to check how many numbers we have. So this is the 0th number, first, second, third and fourth. So if you remember, these are the place values. So it is in 0th place value, tens, hundreds and so on. So now in the next step, what you will be doing is you will have to multiply each individual number with the corresponding base power, whatever place value it has. So it can be written as 2AE 2A E0B base 16. Now, so then since this is 2 is at the place value 4, so 2 into 16 power 4 plus 10 into 16 power 3 plus, why am I writing 10 over here? Because A's value is 10. After that we have E's value is 14, so we will write 14. 14 into 16 square plus 0 into 16 plus B value, which is 11. So B is 11 into 16 power 0, which is equivalent to 1. So this will give us the answer 175,627, which is of the base 10. So these are the expansions from the hexadecimal, from binary and hexadecimal to decimal digits. Okay. Now, when we are converting for base conversions, before that, let's see the digits again. Hexadecimal, octal and binary representation of the integers 0 through 15. So over here, if you see, decimal is the one that we generally use. 0 to 15 is same. For hexadecimal, we will use 0 to 9 and then A to F. For octal, we will be using 0 to 7 and again we will start the number 8 from 10. For binary, you already know how a binary number is represented from decimal number. Now, what about converting to the base B? So suppose if we are giving a decimal, if we are given a decimal number or an octal number, how can we, if we are given a octal or a hexadecimal or a binary number, how are we supposed to convert it into the other form? So let's see that. To convert any integer n to any base b, we have to find the lowest order digit and compute n mod b. Let's see that how we are supposed to compute this. So first and foremost, we are given the number 1, 2, 3, 4, 5, which is of the base 10. What we are supposed to find is octal. We are supposed to convert this number into an octal number. So whenever we are doing that, we are supposed to perform division. So in the earlier case, we were multiplying with the base. Over here, we will perform division. So divide 1, 2, 3, 4, 5 by 8. So over here, we have to divide. Let's do it over here. 1, 2, 3, 4, 5, 8 times. So the answer will be 1543 and the remainder will be 1. So it can be written in this way. 8 into 1543 plus 1, that is dividend is equal to divisor into quotient plus remainder. Okay, so this 1 is a remainder, divisor is 8 and 1543 is the quotient. Again, in the next step, again you will divide this 1543. So the quotient is 192 and the remainder will be 7. So let's write it again over here. 8 into 192 plus 7. After that, we have to keep dividing it until we get the quotient as 0. So 8, it goes 24 times. The remainder is 0. We will just continue it over here and write the next steps later. So 8, 3 times, remainder is 0. And again 8, 0, 3. Okay, so the remainder is 3 and the quotient is 0. So we will write it over here. It can be written as 8 into 24 plus 0, 8 into 3 plus 0, 8 into 0 plus 3. What are we solving? 1543 is giving us this. 192 will result in this. 24 can be represented and then 3 is represented as 8 into. So now what we have to do is we have to take it from bottom to top. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 to the base 10 can be represented as 30071 to the base 8. So this is the octal expansion. That is, every time we have to divide by the base which we need and keep a check of the remainder. So we have to keep a note of the reminders and the remainders should be written in a fashion which is from bottom to top. Similarly, for hexadecimal, let's take an example for hexadecimal expansion. So for hexadecimal expansion, I am taking the number 177130 and right now it is in decimal. We need to find it in hexadecimal, which is 16. So let's begin. Let's directly do it over here first. 177130. Which number we have to use? So we want the base 16. So let's take it by 16. So 16, it goes. You can do it on the calculator also and find the remainder each time. 43 times, the remainder will be 3. Then 2 times, 16 2 is 32. So the remainder is 11. And then 0 times, the remainder is 2. We have to continue it till we get the quotient as 0. So we have to continue this till we get quotient as 0. Now one more thing to be remembered is, whenever we are speaking about hexadecimal expansions, we will have the numbers 0 to 9 and then A to F. So what is the number? Let's write it over here. A will be 10, B is 11, C 12 and so the number which is greater than 9 should be replaced by these alphabets. So let's replace it. 11 is B, 14 is E and 10 is A. Okay, and let's write it over here also. So 177130 is written as 16 into plus 10, 16 into 691 plus 14. This is 11070. Then 691 can be represented as 16 into 43 plus 3. 43 is represented as 16 into 2 plus 11. And 2 is equal to 16 into 0 plus 2. Now, just again, let's change it. This is B, E, A. So now this can be written as 177130 to the base 10 in hexadecimal will be represented as top to bottom. So 2BE, 2B, 3EA, 3EA, which is of the base 16. Okay. And the next one is the binary expansion. So binary expansion will do for the number 241. Binary expansion means I want it in zeros and ones. So in zeros and ones, let's see that. So this is very simple. Let's solve for it. 241, we have to keep dividing it by 2, so it goes 120 times, the remainder is 1. 60 times, remainder 0. 30 times, remainder 0. 15, remainder 0. 7, remainder 1. 3, remainder 1. 1, remainder is 1, then 0, and so we got the quotient 0. Now let's represent it over here. So 241 is written as 2 into 120 plus 1. 120 is 2 into 60 plus 1. 60 is 2 into 30 plus 0. 30 now 2 into 15 plus 0. 15 is 7 times 2 plus 1. Then 7. 2 times 3 plus 1. 3. 2 times 1 plus 1. And then finally 1 is 2 times 0 plus 1. Now let's go from here so we can look over here. We have to go from bottom to top. So 241 to the base 10 can be written as 111, 3 zeros, and then 1. So these are the conversions. We will continue the next in the next class.